I am back, and now we're going to do a technical workshop. So we'll have a lot more, really dive into some technical stuff here. And we're going to talk about hacking vehicles. Some radio hacking, some car hacking, and some hardware hacking. Has anyone seen Gone in 60 Seconds? It's a great movie, great movie. So we're going to learn to be like those guys. So the first thing in hacking a car or getting access to a car is you need to actually get some sort of physical access to that car. So how do we do that? Well, the first thing we need to do is go into someone's garage, because usually cars are in garages. At least in Gone in 60 Seconds, they're usually in garages. So once we take a look at a garage, how do we get into garages? Typically, we have remote controls. So we have some sort of remote control that actually allows us to open this garage. Now, if you take a look at pretty much any remote control for a garage or garage door opener, if you look at the back, there will be some identifiers. Different countries have different regulatory bodies. I'm not sure what it is in Spain or in Europe, but many of them will have something like, will often have an FCC ID, and then I believe here it might be a CE, right? I think you have CE for radio communication. So there might be like a CE ID. Different countries have different IDs. And often that's public information. So with the FCC, that's the, essentially they control radio transmission in the US. So if I take any device, in fact, if we all take our phones out right now and look at the back, we'll see some identifier on the back. So on here I see an FCC ID, I see an IC, so maybe that might be here, and an IMEE, or IMEI. So these are things that we can actually look up online and find information. So I use the FCC because in the US everything has to have an FCC ID. And once we know that ID, we can look it up. So when we go online, what I would suggest is using fcc.io. It's a website where you can type in an FCC ID, even for a phone, for example, and it will show you all of the publicly available information from the FCC. Now, the FCC does all sorts of things when you're trying to register a product that performs transmitting. So a phone is a transmitting device. It transmits voice, data, all sorts of things. So by going to fcc.io from Dominic Spill, he created this, we can see all sorts of things inside. One of the most important things to see is first, let's say we're taking this garage door remote and we want to know, what frequency is it transmitting on? That's the first thing we need to know. So from here we can actually see, I circled in red, it's transmitting on 390 megahertz. So this is a garage door opener I had that was transmitting on 390 megahertz. So just by opening this on FCC, even if you don't necessarily have access to a device, if you can find that identifier, then you can look it up online. Other things that we can see from the FCC ID. There's a cover letter, external photos. So if you're online and you're trying to research something that you don't necessarily have physical access to, you can find external photos of that device. What's cool is there are even internal photos. So for everything the FCC tests, there are internal photos, and we'll see that in a moment. There's a test report, a test setup, and a user manual. Often if I'm reverse engineering or if I'm trying to do some research into a device before I even have access, I'll go look up the docs on FCC. I'll also read through the user manual. Because the user manual might not even be an actual manual, or it might have been a testing manual that they had when they were submitting to the FCC that they decided to modify or redact information. So you might find information in that user manual that you wouldn't find anywhere else. Additionally, the test report shows all sorts of interesting information that you wouldn't access otherwise. So in this test report, we see a couple of things. We see like 390 megahertz, the channel number, the modulation type is ASK. We also see the internal photo. So at the bottom right, you can see the actual photo of the transmitter. So let's start talking about the devices that I'll actually use to reverse engineer something like this. I like to use HackRF1. It's a transceiver. It can receive and transmit. It has a very wide operating range, so from 1 megahertz to 6 gigahertz. you can get raw IQ samples. And what that means is you can basically get full raw radio communication. In quadrature, you can get not only amplitude, frequency, but also phase. So you can do anything with that raw data. It's also entirely open source, open hardware, and it works with GNU Radio. Doing something like a replay attack is super, super simple. I mean, replay attack is probably the most basic of the attacks, but it's literally you can run a command to actually listen to, let's say this is 390 megahertz, and then to replay it, to transmit it. The cool thing about something like HackRF is because you don't need to demodulate it, and you don't even need to know the exact frequency, you don't need to know the baud rate, you don't need to know the modulation. We can scan up to 20, or it can listen to 20 megahertz at a time. So you just have to be within 20 megahertz to actually capture a data. So if you see someone maybe hitting a garage door button and opening a garage door, and you capture it within 20 megahertz, then you can replay that to open that garage door, assuming it's using fixed codes. So this is pretty cool, but we can do a lot more advanced things. Another tool I like to use is called RTL-SDR. It uses a Realtek chip, and it's a much smaller range, so that'll go 24 megahertz to 1.7 gigahertz. You can also get your raw IQ samples. It only receives, but it's very inexpensive. It's like around $20 US. And it's still pretty powerful. It's also nice and small, so it's pretty convenient to carry with you. Another tool that's useful is the GNU Radio. I find this pretty useful, and you can use this to basically work with signals, work with audio, work with radio, and it allows you to basically create flow graphs to take that data and work with it. Another tool that I often use is called GQRX. GQRX allows you is a spectrum analyzer. It works on OS X and Linux only. Allows you to easily and quickly see different frequencies. You can use RTL-SDR or HackRF. You can, let's say, hit the garage door button, and then you'll see a spike in GQRX, and you'll know exactly where it is. If you're on Windows, you can also use SDR Sharp. That's another free tool that's available to you. Also a spectrum analyzer. Another tool I use a lot is called RTL-FM. It's a Realtek tool, and it allows you to demodulate data. So if we're looking at some data, at some FM or FSK or ASK data, you can demodulate it into its actual digital form from raw IQ samples from the radio. It's pretty easy to use. You don't need to know too much to really get started in this radio stuff. Even if you're not familiar with it at all, all you need to know are a couple of commands to really start getting. So if we go back to the FCC docs, and let's find the stuff that I think is actually important to look at. So I would suggest always looking at internal photos. Internal photos are great because then you can see what chips are actually being used or what circuitry. You might be able to see a crystal oscillator. You might be able to zoom in and see what megahertz it's running at. You might be able to see the name of a microcontroller on there, or a certain transmitter, or a radio frequency chip. All sorts of things that you can learn from the internal photos. There's also a test report, which is really important. It can tell you things like the modulation or baud rates. It might also show you graphs, like spectrum analysis graphs, or that you can then use to also determine things like baud rate and frequency. Also, as I said before, the user manual. I think the user manual is super important. You can learn a lot from it. So I always sort of pass through the user manual just to see, is there any additional information I'll learn about this device that I didn't know about before. Here we can see a test report of that actual garage door opener that I use. So here we see it's ASK, which means amplitude shift keying. And you can also see you can actually see an example of it in use in that graph there. And based off that information, we can probably also figure out the baud rate, or how fast each bit is sent. So to understand what ASK is for a moment, we'll take a look at this graph. Basically, ASK is called amplitude shift keying, or ASK. So amplitude shift keying is a type of amplitude modulation, or AM. If you ever go in a car and you listen to the AM radio, that's amplitude modulation. It's the same type of modulation here. It's basically where the amplitude, or essentially the volume of a signal, is going up and down. In typical ASC or OOK, on-off keying, up means 1, and no volume or no signal, no amplitude means 0. It's a very basic way of sending digital data across an analog medium such as radio. Frequency shift keying, or FSK, is another one. If you've ever heard of FM radio or listen to FM radio in your car, FM is frequency modulation. FSK is a type of frequency modulation. It's where you're shifting between two frequencies to basically represent ones or zeros. And there's different types of FSKs where you can have 4 FSK where you can actually represent 0, 0, 0, 1, 1, 0, 1, 1. Here we can actually see 2 FSK on the left. So you can actually see two pieces of signal basically getting sent at the same time. And that's actually swapping these 2 frequencies. So whenever you see that, you can safely assume that you have 2 FSK. On the right, you can see ASK, or ASK, on top, because it's a single signal, it's turning on and off. So based off that information, just by looking, if the test report, the FCC test report, doesn't show you, or you can't determine it from the FCC, then you can use this information. Now, if we actually record this data from this garage door, we can open it as a WAV file. We actually get a WAV file that you can then open in Audacity or any signal processing software. So here, I've recorded it. You can see it's basically a signal getting sent a bunch of times. And I've zoomed into one section of it where I see binary. I basically see long signals and short signals. Now, if I see those long, high amplitude, high volume areas, and I consider that a 1, and I take the shorter ones and I consider it a 0, it actually matches up with the actual pin inside of the garage door opener. So if you've ever opened up one of these garage door openers and you see those 10 dip switches or 12 dip switches, we can see that equates to this fixed packet here. This is essentially a packet that never changes. So just by listening to radio frequency, we can figure out what those pins are switched to and set our own garage door opener to that. Now, if we take a look at this and think about this in binary, let's say we get one of these switches and we only have 12 bits, right? If there's 12 switches or 12 binary dip switches in there, that's 12 bits. 12 bits is not very much, right? That's something like 1,000, 2,000, there's probably 4,096 possible combinations to actually produce 12 bits. So if you have a garage door that has a pin like this, that means your garage door has 4,000 possible passwords. 4,000. In comparison, if you take a 2-letter password and a 2-letter password is about 5,000 possible combinations. So if you have a bank account or something that allows entry into something and a 2-letter password, your 2-letter password is more secure than the most secure fixed code garage, 12-bit garage opener. Now, if we were to brute force this 12 bits, it would take approximately 30 minutes to actually transmit every possible 12-bit code. But let's take a look at these transmissions a little bit more. First, on each transmission for a normal garage door opener, it'll send the same signal, same sequence of bytes or bits 5 times. So you'll see 5 times the same exact signal. But most garages will actually listen to the signal and see the signal the first time. So it's only resent in case there's some sort of interference or accidental jamming. So if we actually cut it down instead of 5 times and we only send it once, then we'll actually get it down in 6 minutes. So we've now gone from 30 minutes to 6 minutes just by reducing the repetition. Another thing we can do is that if we see before, there's basically periods of wait time where there's no signal for about the same amount of time that there is signal. If we actually cut that signal out, if you see in red, there's on the top line, there's a period of time where there's no signal. If we cut that out, then we've just saved half the time. So we can reduce the amount of time it takes to brute force a garage that we know nothing about, and open it in half the time. So you can now reduce down to 3 minutes. Now, another thing while looking at this was if there's no space between two different codes, how does the garage door opener know where one code begins and another one ends? There's no way for it to really know where one code starts and another begins. If you're online, for example, and you go into a password prompt and you type a password in, you hit return, it will send that password in a packet and say, this is the password. But in radio, for example, if there's no other data delineating the password from some other data, then I can assume that we can assume that it doesn't really know where the beginning is and where the end is. So perhaps it's using something called a bit shift register. In a bit shift register, what we're doing is we're taking a series of bits and we're shifting it one bit at a time into a register. So let's say we send a 13-bit code, as I have below. If I send 13 bits, but the bit shift register only supports 12 bits, it will put all 12 bits in that bit shift register, and then it will test, is this 12 bits the correct password to the garage? If it's incorrect, instead of removing all 12 bits and then taking in the next 12, it only shifts by 1 bit. So I can send 13 bits and actually test two 12-bit codes. So I've just tested 24 bits by only sending 13 bits. So there must be a way that we can exploit this, effect of a bit shift register so that we can send every possible code without sending every possible code, if we can actually overlap. Because again, 13 bits can test two separate 12-bit codes. So one of the things we can do here is something called the De Bruijn sequence. De Bruijn is a mathematician who created this algorithm to efficiently calculate an overlapping sequence. So in here, let's say we had something that was only 2 bits. If you wanted to test every 2-bit sequence, 0, 0, 0, 1, 1, 1, 1, 0, that's 8 bits total. But if you can see here, let's just say I take the 5-bit sequence 0, 0, 1, 1, 0. That actually contains every 2-bit possibility. Right? The first 2 bits are 0, 0. Then the next bit together is 0, 1. And the next bit together is 1, 1. And finally 1, 0 in the end. You can see they all overlap. This 5-bit sequence overlaps to create 8 bits total. And a 2-bit shift register will actually see every possible 2-bit combination in this 8 bits. So we can actually exploit this property to open a garage that would normally be 12 bits, that would normally take 30 minutes, down to 8 seconds. So unfortunately, every fixed code garage, about half the garages out there that exist, can be opened in 8 seconds by exploiting this property. Again, by taking those 12 bits, those 4,096 possibilities, and producing an overlapping sequence, you reduce the amount of time immensely that it would take to actually open this. And this happened with every garage I tested. Unless it was using rolling codes, this exploit works. So now let's talk about how do we actually test something like this. One of the devices that I used quite a bit was Yardstick 1, another device by Michael Ossmann. And this is basically a sub-GHz transceiver, so it can transmit and receive. It's not software-defined radio. It's unlike RTL-SDR or HackRF in that it performs modulation and demodulation on the chip. You can't get raw IQ samples, but it's very effective and very efficient to use if you know what you're looking at. So if you know the modulation, for example, from the FCC report or from using RTL-SDR. Another tool I like to use is called RFCat, and it gives you a Python interface into the Yardstick 1 sub-GHz transceiver. So it allows me in a couple of commands to start transmitting, receiving anything in the sub-GHz range. So that means I can start talking to garages, I can start talking to cars, I can start communicating with pacemakers, watches, all sorts of things are in the sub-GHz range. So there's a lot of interesting stuff to look at there. And this just makes it easy. It's like you're at a terminal, you type a couple commands, it'll modulate everything for you, it'll send it. Because you're in Python, you can loop, you can convert information, digital data. It makes it very easy to work with. Another tool comes from this company. I touched on this a little earlier, but the Mattel IM-ME. So this is a toy that's originally for children. And basically, it allowed communicating or texting using this pink pager. And this pager has a Texas Instruments chip inside of it called a CC1101, which is also a sub-GHz transceiver. But what's cool is a bunch of people figured out that you can actually hack this toy and you can modify it to do anything under sub-GHz, to transmit on anything and to receive on anything. So here you see Michael Ossmann's spectrum analyzer running. So this was actually able to see everything under 1 gigahertz. So if you hold this and let's say have a garage door clicker and you click that clicker, you'll actually see the frequency that that clicker transmits on in this device. And what's cool about this is because Mattel is such a big company, they've created so many of these, which ultimately became discontinued. So they're cheap on eBay. You can find them for $20, $30 US. And now you can hack it, modify it, load your own code, and have it be a pretty powerful device that otherwise might cost $100 to actually create. Also, another tool I used was GoodFet. So in my demonstration, I created something called Open Sesame, and I used the Mattel IM-ME. I loaded the code. I used the De Bruyne sequence and exploit that I talked about, and I actually was able to open virtually any fixed code garage that I tested this on. I used the GoodFet to essentially program the device. And here I think we can, let's see if it'll actually show. So I just went up to a garage, hit space, and it just opens. Literally within 8 seconds of any fixed code garage, it simply opens. Nicolas Cage would be proud. Unfortunately, after I released this code, the price shot up for these handheld devices. So I did break the code so that it wouldn't simply allow thieves or criminals to open garages, but I left most of the code intact on my GitHub so that people could inspect the source and see how it works. So some lessons when you're actually developing technology like this is don't use a really small key space, and also require some sort of preamble or sync word. So this means a preamble will say a password is coming up. And that way, the De Bruyne attack won't work. You won't be able to sequence, you won't be able to line multiple passwords up. You have to have a preamble, password, preamble, password. Another thing is using rolling codes. So now we're inside of a garage, and we have at least some sort of access to cars. So what can we do here? Well, a ton of cars are connected now, so that's pretty cool. There's probably something we can exploit there. So what we can do is, one of the things I've looked at is OnStar. OnStar has a pretty cool mobile app. And what you can access from there is you can see the vehicle location at all times because the car itself has a cellular connection that's always connected. So you can see the vehicle location, and you have access to a bunch of things. The vehicle status, so information about how many miles it's been driven. You have access to a key fob, so you can actually lock and unlock the car. There's even a remote start feature, so you can remote start the car from this app, as well as hit the horn, the alarm, and other information. Now, because this is a mobile app, it must be talking to some server. So I installed a certificate authority on my mobile device to start seeing what is this OnStar device sending, and performed SSL man-in-the-middle attack, and finally was able to sniff what it was sending. And quickly I saw it was sending basically the username and password in the clear. This is after it was base 64 decoded. And then in my testing, I had realized that I actually forgot to install the certificate authority. This was a different device I was testing. So normally when I'm doing an SSL man-in-the-middle attack on a device, I'll install a CA, I'll install my own custom CA, I'll perform the SSL man-in-the-middle, and then I'll sniff. But because I forgot to install the certificate authority, the app should have complained and not allowed the man-in-the-middle attack. However, because they weren't actually doing certificate checking or SSL certificate checking properly, I was able to do the man-in-the-middle without any certificate authority at all. That means an unmodified device, an unmodified iPhone, can get attacked. You can perform an SSL man-in-the-middle attack on and extract someone's username and password. And because it's always sending either the username and password or authentication, you can, once you get that once, you can then log in indefinitely into that car, literally into that car. So what I used to perform this attack was a Raspberry Pi, a GSM board, because if I'm going to do an SSL man-in-the-middle, for their phone. Whenever their phone gets near the car, I wanted to do an SSL man in the middle, but also give them internet access so that it can still communicate with the server. So I used Mallory, which is an open source SSL man in the middle software for Linux. DNS spoofing so that I'm only doing that SSL man in the middle for GM servers. GM owns OnStar in the US. So the cool thing here is that if you go to Google or Gmail or something else that has SSL, I don't actually perform interception there. So you don't notice anything's wrong. IP tables, I also used an Alpha card for Wi-Fi and an Edimax Wi-Fi dongle as a SIM card. Now, the next thing I need to do is actually, if I'm attacking a car and I attacked a friend's car, is I actually need to perform that SSL man-in-the-middle attack, their mobile device needs to be on my network. So how can I get them to join my network? It's a little unreliable to hope that they actually join my network. That will probably almost never happen. However, there's a pretty cool thing that mobile devices do, and that's they send probe requests. So if there is no server or Wi-Fi router AP that they see that the mobile device normally jumps onto, then it sends a probe request and it says, hey, does this network exist? Does this network exist? What it's actually doing is it's telling us the name of the networks that it normally joins on. So by using that information, by sniffing that information out of the air, I now know the name of a network your mobile device would normally join on, and automatically, dynamically, I generate that network. So if your phone says, I normally join a network called CyberCamp 15, this device simply says, okay, take CyberCamp 15, generate an open network with that SSID, CyberCamp 15, and now send a request back to the phone, or a response back to the phone, saying, hey, I'm here. And now the phone joins that, and now you can perform the SSL man-in-the-middle attack. So the hardware, very little, very inexpensive, less than $100. Put it together. I called this device OwnStar, and I used it on a friend of mine who had a GM vehicle. So I put the Raspberry Pi and GSM under his car, waited until he opened it. It sent me a text message to let me know, and then I was able to test it on him. So here you can see it unlocking, and then after that, I can start the vehicle, and literally I'm able to unlock and start the vehicle from there. All because of that small combination, really because they're not actually validating certificate authority. Absolutely crazy. So lessons to learn: if you're going to be doing secure, communication with the server, always, if you're using SSL certificates, always validate the certificate. Better yet, you can actually use certificate pinning and ignore CAs altogether. I keep hearing about certificate authorities that are getting hacked or CAs that are getting invalid or basically, for example, Dell. I think just this week we found out that Dell was issuing their own CA on new Dell computers that you buy. So that means Dell is capable of intercepting all sorts of traffic. So if you use certificate pinning, then you avoid the CAs altogether. Another thing is if you're going to use passwords, don't do it in clear text. Hash it, use the salt, make it hard to crack if someone ever gets access to it. And I think lastly, always assume you're on a hostile network. If you're doing some sort of secure communication or you need to communicate with another server, always assume you're on a hostile network. Someone will be hostile at some point, whether they're attacking the network, whether they're attacking GSM, whether they're attacking Wi-Fi, whether it's a jailbroken phone, whether it's a hacked phone. There's so much that can be attacked. So now that was a pretty cool attack or at least a fun attack on IoT. But there's another thing that virtually all cars have, and that's key fobs. So there's some fun stuff we can do here. So I've done some key fob research over the summer, and one of the things I started doing was looking at how they work. And primarily they're working from rolling codes. Now often what I'll do is I'll use the FCC ID, or I'll open the key fob up and I'll look inside, because I want to see everything inside. And usually there's a transmitter and a microcontroller in there. One of the things I kept finding was that a lot of them were unknown chips. They would actually mark off. They would remove the markings from the chip because they didn't want people to know what was being used. So one of the things that I had to start doing was figuring out what chip is being used inside, even though it has no label at all. So the tools I used the logic analyzer in many cases. A logic analyzer allows you to do digital logic analysis on chips, so you can see digital ones and zeros moving really quickly. I also got sort of SMD Micro Probes, so for surface mount technology, because the normal probes that you might get are not going to be, they're going to be too big for like small chips like that, like WQFN and other sort of like flat package or small, very thin pins. I also test pins with a voltage meter or a multimeter. So what I want to do is, if I have a chip that I don't know what it is, I start testing voltage on every pin, and I can connect the ground to the actual ground of the battery. That's the ground. So I know where to connect the ground. I connect the positive to every pin, and then I start mapping it out. So I start mapping out where I see ground. Every pin I see ground, and then every pin I see voltage. Once I know all of that, I'll go back. I'll use the logic analyzer to connect to a bunch of pins, and then I'll measure. I'll take a look at that data as well, because I might see something like a clock or something like a square wave, and I can assume that's a clock, and then I can map out. I can say one pin is the clock pin. So once I've done all that, then I'll say, okay, well, I know this is 2.4 gigahertz, for example, just because you can use a spectrum analyzer like HackRF, right, when you're pressing the key fob and see what frequency hits. Once you know that, then I'll look up all of the data sheets I can find on, let's say, 2.4 gigahertz transceivers or transmitters. So there might be a Cypress chip, a Nordic chip, Microlinear, Hope RF, Texas Instruments. And then I start, let's see if I have it here. I'll start matching up pins. So I'll actually go through all of these data sheets, and I'll look at all of the pinouts and find the ones that have the first package type, the same amount of pins, and then I can start matching up the actual pinouts. I can say, oh, well, this one has ground here and ground here. It has voltage here and voltage here, clock here, clock here. So then I know that that chip that had 0 markings was an ML2724. From then on, I now know what every other pin is. So I can use the logic analyzer to start analyzing every other pin. I can say, okay, well, this pin is clock, this one might be data, this one is serial, data in, data out, and I can start extracting all of that communication. From here, I'll monitor all of the serial communication, SPI, I2C, UART, USART. For something that's frequency hopping, then I can actually see the timing. I can see how often it actually frequency hops. I can see what that pattern is. I can see what frequency it's hopping to. Is that following a simple pseudo-random number generator? I can detect the modulation, because now I can look at the data sheet. Now that I know what chip it is, I can look at the data sheet for that chip, and I can look at everything about that chip. I'll know the baud rate, I'll know the modulation, and I can see all of the data being transmitted. Sometimes I may want to intercept that device, so then I'll use either, if I can get my hands on the same chip, I'll use the same chip, or I might use something else like an RF CAT or Yardstick 1. I like to use the teensy device a lot. It's kind of like it's an ARM-based chip, very small, very portable, works with the Arduino environment. You can do a lot with that. Sometimes I'll intercept a chip, so I'll actually cut a pin and then tie it to my device and then tie that back to the actual chip. That way I can do on-the-fly sort of man-in-the-middle attacks on the communication between my circuit and the car, for example. One of the chips that I was looking at was the high security. So I was looking in my car, actually. It was using this chip called NM95HS01. It's called the high-sec, high-security rolling code generator. And when I sniffed it, it looked like this, except the data kept on changing. So in our garage attack, I was able to learn the code or just brute force through all codes. Unfortunately, with cars that are using rolling codes, the code is very long, so we don't have enough time to brute force it. It would take years. Additionally, the code changes every time. So even if you're able to sniff that code once and replay it later, it will not work. The car will actually say that this code only works once. So let's understand how rolling code works. So basically, there's a random number generator in the key and the car, and they're actually synced to each other. So whenever you press the key, it sends a signal, a unique identifier, to the car. The car receives it and unlocks. Now the car says it will never use that again. So if an attacker was outside listening and they replay it later, the car will ignore it. It'll say, I've already heard that code before. You need to tell me the next sequence, the next ID in the sequence. Now you might think, okay, well, what if I have the key fob in my pocket and I accidentally press that key fob a bunch? And then I go to my car, will I be out of sync? Fortunately, one of the things the cars do is that they'll actually have a rolling window, a window that allows you to be out of sequence forward by some number, so maybe 500. So you can actually press it 500 times before you're out of sync with the car. So this prevents replay attacks. However, there is something interesting about these rolling codes, and it's that if you can capture the signal while the remote is out of range with the vehicle, you can replay it because the car never heard it. And rolling codes don't have an expiration. They only expire after a future code has worked. So if I can, let's say, go into your house, press the button when it's not near your car, and listen to that, I can then replay it later. However, this is a lame attack because I've already broken into your house. Like, I might as well just take your keys. So how can we actually exploit this? Is there a way we can exploit this rolling code? And we can with jamming. So what's interesting is, let's take a look at this graph here. This basically in the red square is the car's receive window. So we have frequencies on the x-axis, and the car receive window is pretty big. Like, let's say the car listens at 315 megahertz. Really, it's probably listening between 314 and 316 megahertz. So you can transmit the data anywhere in that 2 megahertz of space or bandwidth. Now, your actual key is the purple. It's the signal. So when you hit the key fob to unlock your car, it'll send that signal on 315 megahertz, let's say. Now, if I jam at slightly lower, let's say 314 megahertz, the car will also hear it because the receive window is so big of the car that it will hear both my jamming and you unlocking the car. Because it hears two pieces of data simultaneously, the car demodulates it as one piece of data. So those two pieces of data combine into one, and that just becomes invalid data, data that the car cannot understand. What's cool, though, is if I'm jamming at a slightly lower frequency, like 314 megahertz, and then I'm listening myself with my own receiver at a much tighter frequency in the light blue, I can hear what the key fob is pressing. So when you press your key fob to unlock, I'm jamming. Your car doesn't hear it because it gets confused with my jamming signal, but my own receiver is able to listen to that short window or that very tight window and listen to the rolling code of your key fob. The problem is, let's say I now have a unique rolling code that your car never heard. So I can actually go back and I can replay that code and unlock your car. What prevents this attack is that every time you actually do unlock or lock your vehicle, all previous rolling codes are gone. They stop working. So the way it works is I need a code in the future to work. So what we can do is we can actually do this twice. If I jam and then I listen and you press the button, it tries to unlock and it doesn't unlock, what do you do? As a user, I now have a code that I can use, but it's about to get ruined. But if you're a user and you try to unlock your car and it doesn't work, what do? You hit the button again and you try to unlock it again. Now, if I've jammed for both of those sessions, I now have two different rolling codes, a previous one and a future one. I can then replay the first one, and now I have a future code that will work. So because I'm replaying the first code upon your second try, I now let you into your car where you can drive away, and I have a code in the future that your car will respect, and then I can replay that. So using this, we can easily exploit a car. Another thing that I found is that a lot of these cars, the rolling code is entirely separate from the key you press. So let's say you press the key to unlock, or let's say more realistically, you press the key to lock. Now, if I've listened to that, what good is it for me to replay a lock command later on? It just means I'm going to lock your car again. But as an attacker, that's not very interesting. However, because the rolling code is separate from the data, the button you press, As long as I have a valid rolling code, I can adjust the data bit, the bit that says unlock, lock, trunk, alarm. So I can actually convert a locking bit, something that says lock the car, to an unlock just by flipping that bit but using a valid rolling code. So they don't actually hash that data along with the rolling code. Really, they should be encrypting that stuff together. Here's a very basic example of, here's a tool I created called RollJam, and it uses a TNC 3.1 and two CC1101 sub-GHz transceivers. It's about $30 US to build. One of the transceivers is jamming, and it only jams once it starts detecting a user unlocking their car. So it's not constantly jamming. It literally jams for milliseconds at a time. And then the other receiver, the CC1101, is also receiving to listen to the actual code while it's simultaneously jamming, preventing the car from working. And with that, I was able to open basically every car I tried. So that was pretty exciting. And this is on 2015 vehicles. On every car I've tried, even the newest and latest and greatest models, I was able to unlock these vehicles using this attack. So this attack has technically been around forever. It's never been applied here, or at least never demonstrated. So RollJam, I have information online, just how Nicolas Cage gets into this kind of stuff. And the lessons that we've learned, there's a couple things. If you're designing a system like this, there's a couple things you want to do. First, you want to encrypt or hash the information that you have. You don't want to just have a rolling code and then a field that says lock or unlock. All of that information should be encrypted or hashed together so that they're intrinsically tied together so that you can't abuse it if someone is ever able to recover some of this information. You can also do an HMAC to prevent bit flipping. Using something that has time involved is also good. If you put, let's say, a real-time clock in the actual key fob, then you can actually distribute keys and you can say, all right, this key is only good for 1 second. That way, if an attacker is able to access that key, it will only be good for 1 second. And there's no point of unlocking someone's car within the same second they unlocked it. I mean, you're just doing them a favor. Another way is to challenge response. So inside of your key fob, you could have a receiver and then just do a challenge response where the key fob will say, hey, I want to unlock you. The receiver will say, okay, the car will say, okay, well, here's a challenge, and then your key fob can respond. A lot of cars actually do have receivers and transmitters in there. So that's pretty cool. That's something that can be implemented today. Dual key lock is actually something that exists today that is also capable of doing receive and transmit, or of doing a rolling code that prevents this attack. However, I haven't seen any single car use it. So that's it on the technical side. Thanks so much. Does anyone have any questions? Thank you. Oh, thank you. Okay, thanks.
Sí, tenemos tiempo para un par de preguntitas nada más, ¿eh? Adelante a las preguntas.
Oh. Okay.
Hello?
Hello.
Yeah. So, my question is a little bit to how to get into the detail. So, outside of a controlled environment, let's say we really want to open some stranger's car. You say you jam the first rolling code, the second rolling code,
Correct.
and you send the first code.
Correct.
But the thing is, you are jamming both codes. Would you delay after the second jam and send the first key? Would the victim maybe realizes about that delay? Like, how do you switch off the jamming to actually send the code?
So you're jamming for two codes, right?
Yeah.
So upon the second code being received, the device automatically stops jamming and then replays the first code.
Yeah, like a bit of delay, right?
I mean, it takes less than 100 milliseconds.
Okay.
So
okay.
Yeah, it's to the user, it's instant.
Okay. Thanks.
Sure. And yeah, I mean, all of my tests were not in controlled scenarios. They were in active environments with me breaking into my friends' cars. So, Any other questions? Yes. If we have a over here. I think someone.
One of the keys of your success into hacking for the GM car with a mobile application was because they didn't validate the certificates.
Correct.
So what would you do in case the application would validate who emitted the certificate? Will the man-in-the-middle attack be feasible?
No. If they're doing certificate validation, then that specific SSL man-in-the-middle attack would not be feasible. I would have to find another attack. So another thing to note is that many companies had this issue. After I looked and saw GM OnStar had it, I found BMW had it, Mercedes-Benz, and Chrysler. All of them had this issue. So I was able to perform the same attack on BMWs, Mercedes-Benz, and Chrysler vehicles on top of the GM. If I had found that, let's say, for example, that it didn't work, let's say they did do certificate validation, you just need to attack the network somehow. So maybe what I would do is, instead of getting the person to join my Wi-Fi network, I wouldn't have a Wi-Fi network. Instead, what I would probably do is I'd probably jam 3G communication so that their mobile device is then downgraded to 2G. 2G has already been hacked, so I can easily intercept that 2G communication, have them use essentially 2G or GPRS so when they're on the internet and they use that app, I can now intercept that communication. That would probably be my immediate next test.
Maybe the fact that car makers are not able to deploy CAs and validation is the motivation they use not to validate those certificates. I mean, in case CA would be compromised, they should roll out a certificate invalidation. So maybe that's why they aren't using it.
Yeah, but I don't think that's a very good reason. I mean, that's a much worse reason than they have two decent options. They can either do certificate pinning, where they generate their own certificate and they don't depend on any CA. Of course, as you said, they won't be able to reject certificates in the future, but that's better than accepting all certificates, right? I say you're saying you might as well accept a known valid certificate now, and in the future, maybe that gets compromised and you accept other attackers who have it, but today you accept everyone who has it. So
yeah, that's true.
You don't gain anything by doing that. Or alternatively, you can use a CA and depend on them and hope that they don't get compromised. Again, you still have that benefit of time.
Yeah, thank you.
Thank you.
We have to finish.
Okay.
Thank you
very
much
you, everyone.
for being here today. Thank you. Thank you, Samy. Por concluida, por lo tanto, la primera jornada de plenarias en el auditorio, pero esto no ha hecho más que empezar. Además, os recordamos que nos podéis seguir a través de las redes sociales, que también tenemos una aplicación móvil y que tenemos el concurso de Instagram. Así que mañana os esperamos aquí con más ponencias, más charlas, más talleres. No nos falléis. Hasta mañana.